This is part 2 of a 2-part video series on streetlight plans and streetlight calculations for civil engineers. In the first video, we created the streetlight plan in AutoCAD. This video will walk you through the process of laying out your streetlight wiring, calculating the voltage drop in your system, and sizing the streetlight wires. I've created a schematic showing the streetlight system from the last video, showing the lights, the control cabinet, and the pull boxes. I labeled each individual light, giving it a number and indicating the circuit to which it belongs. I have also numbered the pull boxes so we can reference them easily. Lastly, I included the lengths between the various lights and pull boxes, as we will be using these in our calculations. You can see a length of 50 feet from each light to its corresponding pull box. This represents the distance from the pull box to the light base, the height of the pole, and the length of the mast arm. Let's jump in and start laying out the wires. We can start with light LA1. We will need to run an A circuit hot wire from the control cabinet to PB1 and then PB2, and finally to LA1. The hot wires will be shown in red. Running a hot wire to the light does nothing unless we run a neutral, allowing the electricity to complete the circuit. The neutral wires will be shown in black. Now that we've completed the circuit, the light is energized. This video assumes you have a fundamental understanding of circuits. If this is not the case, I would suggest you get a basic understanding of how circuits work before you design any streetlight systems. The video shown here on the screen provides a great explanation of basic electrical circuits. You can follow the link to this video in the description below. Okay, so let's move on to the second light. That would be LA2. We will connect onto the hot A wire in PB1 and run that wire over to PB4, continuing on to LA2. We will also run neutral wire back to PB1 to energize this light. Okay, so we've energized the A lights. Now let's start working on the B circuit, starting out with light LB1. We need to run a hot B wire from the cabinet to PB1 and continue to LB1. We are going to represent the hot B wires in blue. We can connect the neutral for LB1 to the neutral wire that is already in PB3. The A and the B lights are going to share a common neutral. That's why we call it a 3-wire system, because we have 2 hots, the A and the B, and a single neutral. Okay, and so now that we have the neutral connected, LB1 is energized. We should take a minute to discuss this system. We are assuming a split-phase 3-wire system here. This is a typical power supply for residential and light commercial applications in the US and Canada. The service consists of 2 hot wires and 1 neutral. The hot wires have a voltage of 120 volts that are out of phase by 180 degrees. This means their sine waves are mirrored so that at any given time, they will be exactly opposite the other. When one hot wire is positive 120 volts, the other is negative 120 volts. The video shown on the screen here, created by the Engineering Mindset channel, does a really good job of explaining this in detail. You can follow the link in the description below. The reason this matters to us in this application is that we will be using both hot leads for our streetlight system. The A light circuit will use the first hot lead, while the B light circuit will use the second hot lead. Even though the A and B light circuits use 2 different hot leads, they share a common neutral wire. If we have additional circuits like C and D, then they will also alternate between the two hot leads. So you would have A and C connected to one hot lead, while B and D would be connected to the other. Connecting the A and B circuit to a common neutral will have an impact on the voltage drop calculations, but we will go into that later. For now, let's keep going with our wiring layout. The last thing we need to do is run the wires for light LB2. That's the last light on the B circuit. We will connect to the hot B wire in PB3 and run it all the way over to PB5 and continue to LB2. We will extend the neutral wire from PB4 to PB5 and continue to LB2, energizing the light. Lastly, we will show the ground wire in green. This completes the wiring layout for the system. If we go back to our streetlight plan from the last video, you can now understand why we show 3 wires in the sections of conduit that power both A and B lights, and 2 wires in the sections powering only a single A or B light. The 3 wires include a hot A wire, a hot B wire, and a neutral. The 2 wires include either a hot A or a hot B and a neutral. Okay, so let's move on to the voltage drop calculations. Before we get into the calculations, let's take a minute and look at the equation that we'll be using to calculate the voltage drop. The equation is V equals I times R. That's voltage is equal to current times resistance. Let's dissect the current term of that equation real quick for our application. We will convert I into amps per light times the number of lights. So then the I term becomes I times N. So then our equation becomes voltage equals amps per light times the number of lights times resistance. Now let's go in and dissect the resistance term. Resistance is in ohms. And for our application, we will be looking at the ohms per 1,000 feet of wire. So we'll take that ohms per 1,000 feet, multiply it by the length of the wire, and then divide that length by 1,000. So the R will turn into resistance in ohms per 1,000 feet times the length divided by 1,000. So now our equation is volts is equal to amps per light times the number of lights times resistance in ohms per 1,000 feet times the length of the wire divided by 1,000. Let's talk about the resistance in ohms per 1,000 feet. These values are widely available on the internet. I'm going to focus on the wire sizes number 4 through 14 because those are within the range of what I'll be working with on my streetlight system. And then over to the right, you'll see we have a column resistance in ohms per 1,000 feet, and we will be focusing on copper. Typically, your streetlight systems are going to be using copper wire. Now, the second thing we need to think about is typically our lights are specified in watts, not amps. You can see on this example, we have some streetlights, and they've specified that these streetlights are 100 watt streetlights. To convert, we use the equation amps is equal to the number of watts divided by the voltage. So for our case where we have 100 watt light, we're working in a 120 volt system. 100 watts divided by 120 is going to be 0.83 amps. We'll be using this conversion in our calculations. Okay, so let's go ahead and open up Excel and start looking at the voltage drop calculations here. You can see on my screen I have the calculations on the left and the schematic on the right. And you can also see that I've put in the equations that we'll be using for these calculations. We have the voltage drop calculation, how to convert from watts to amps, and the table for the various resistances for different wire sizes. And if we scroll down, we get a table representing the voltage drop calculations. Okay, so the first thing we need to do, oh, and by the way, if you want to follow along and do these on your own, you're free to download this spreadsheet off my website. If we go into this table, the first thing we need to do is identify the circuit number. So let's start out with circuit A. And you'll be doing these calculations on a circuit by circuit basis. So the first thing we're going to do is calculate the total voltage drop for the A circuit. And then we'll copy this whole table and paste it down below and do the voltage drop calculations for the B circuit independently. Let's go through this table column by column. The first column is going to be the section. So that represents the section of wire. So like for instance, if we look at our schematic, our first section of wire is going to be the section from the cabinet to PB1. That's this red line right here. Okay, so let's identify that section in our column. That's going to be cab to PB1. The next section of wire is going to be the section from PB1 to PB2. And then we can identify the section from PB2 to LA1. And then I'm going to go ahead and fill in the rest of the table. We've identified all the A wire sections. Now let's move on to the number of lights. What this represents is the number of lights that are being energized by the section of wire at hand. So like for instance, on this top row, we have the section of wire CAB to PB1. Well, that is energizing both LA1 and LA2. This wire is carrying the electricity from the cabinet to PB1. Some of the electricity is going back over to LA1, and some of the electricity is going back over to LA2. So this section of wire right here is energizing 2 lights. Our next section, PB1 to PB2, that's only energizing LA1. So that's going to be 1 light. PB2 to LA1 is again 1 light. PB1 to PB4 is only energizing LA2. So that's going to be 1 light. And then PB4 to LA2 is only energizing 1 light. So that's going to be 1. I don't know why I entered this row twice. I'm going to go ahead and delete that. Okay, so let's move on to the second column. That's going to be watts per light. Every one of these lights is specified as 80 watts. So we can basically go through every row and enter 80. Okay, so you can see here once we enter the watts, the number of amps per light is automatically calculated in the next column over to the right. For our previous discussion, that calculation is based on this equation. I is equal to watts divided by volts. If you look at this calculation, we basically take the wattage, divide it by 120, that's our voltage, and we end up with amps. We need the amps for our calculations. Okay, so we continue moving right, and we have distance. Okay, so CAB to PB1 is 8 feet. That's just the length of the wire. PB1 to PB2, 24. PB2 to LA1, 50. PB1 to PB4 is going to be 156, so I'm just going to do this in Excel. 156 plus 180, 336 feet. And then PB4 to LA2 is again 50. And then we are using number 10 wire for all of these wires. That's our beginning assumption, because that's the minimum wire that the city will allow. And then you'll see to the right, in the resistance column, the value is automatically calculated. It's using the wire size to find a corresponding resistance using the V lookup equation in Excel. And last but not least, once we've entered all this data, the voltage drop is automatically calculated. These are obviously very small voltage drops, and that's not surprising because this is a small system. You'll notice that we have this table separated into 2 parts. The part that we just completed was the voltage drop for the hot A wire. Now we need to go on and calculate the voltage drop on the neutral wire, because the electricity is losing voltage on its journey from the cabinet out to the light, but then it needs to make a return journey on the neutral wire back to the cabinet. We are losing voltage on both trips. So for this neutral wire table, I'm going to basically copy all of these wire segments, because each of these hot wires has a twin neutral wire. Now, some of you are probably going to ask, why don't we take this voltage drop equation and multiply it by 2? You could do that if you were not sharing a common neutral, and we'll get into that in a little bit. It's a little bit tricky. Okay, so for these calculations, I'm going to calculate the neutral wire separately, and you'll see why in just a minute. Okay, I'm going to leave off the number of lights for now, but let's go in and fill in the rest of the table here. So the way that we're going to fill in the number of wires for the neutral wire is we're going to list the imbalance between the A and the B lights. On the CAB to PB1 section, we are carrying 2 A lights and 2 B lights. So because we have 2 A lights and 2 B lights, those A and B lights cancel each other out. It's a balanced load. So the number of lights on this CAB to PB1 neutral is 0. Okay? Bear with me for 1 second while I go into an explanation on how this works, because this is extremely counterintuitive. At least it was for me when I first learned it. Okay, so let's look at this simple schematic here real quick. We have a single A light and a single B light. This would be considered a balanced load. Both the A and the B are connected to a common neutral. Let's say we have positive 120 volts on the hot A wire and negative 120 volts on the hot B wire. The electricity is going to be flowing from the neutral into the A light and then traveling back to the service point on the hot A wire, because the electricity is attracted to a positive charge. The electrons are negatively charged, so they're going to be attracted to this positive voltage. Now the hot B wire, since it's negative, is going to push electricity. The negative charge is going to repel the electricity. Electricity is going to flow from the hot B wire through the B light back to the neutral wire. So the B light is going to be pushing electricity in a clockwise direction onto the neutral. You have 2 opposing forces on the neutral wire right now. You have electricity flowing in 2 opposite directions for these 2 lights. This is impossible. So what happens is the A light and the B light come to an arrangement, and the B light says, hey, I'm pushing out electrons. And the A light says, well, that's great because I'm pulling electrons. And so the B light says, well, why don't I give you my electrons? And the A light says, that's great, I'll take them. So what ends up happening is you have the flow of electricity go from the hot B into node 1, but then instead of returning on the neutral, they go straight over to the A light and return on the hot A. So then you have 0 current on the neutral wire. And if you have no current, then you don't have any voltage drop. Now, if we switch the polarity, and let's say that the hot A is negative 120 and the hot B is positive 120, and remember this is AC current, so the polarity is switching 60 times a second, going from positive to negative 120. Then we have the exact opposite flow direction. The A light is going to be pushing electricity into the neutral, and the B light is going to be pulling electricity from the neutral. Now, some of you will be thinking, now you're pulling 2 lights off of a single wire. Originally, when we did the calculations for the hot A wire, it assumed that the current in this wire was equivalent to the current for 1 light. Well, what is the voltage difference between these 2 wires? It's positive 120 volts to negative 120 volts. So really we have 240 volts difference between the 2 wires. If you go back to our equation to calculate the amperage, you take the watts of the light divided by the voltage. We have doubled the number of lights, but we've also doubled the voltage. So yeah, you're pulling 2 lights of electricity across this wire, but by doubling the voltage, you are cutting the number of amps in half. Basically, using 240 volts between the wires reduces your amperage on each light. So essentially, you're left with 1 light's worth of amperage flowing through this wire. So our calculation for the voltage drop in this hot A is still valid. Now let's look at what happens if we add a single extra A light on this system. We're going to run a hot A wire over to this light, and then we're going to run a neutral back to node 1. So the A circuit is going to be pushing electricity through the A lights back into node 1, and the B circuit is going to be pulling electricity from the node back to the source. And again, A and B honor their original agreement, but you have this loner A, the unbalanced A, pushing electricity into node 1. Nobody wants to take the unbalanced A's electricity, so it has to return back on the neutral. Okay, so with all that in mind, let's go back to our calculations and our schematic. The main takeaway from the discussion about how the circuits work when we're working on a common wire between the hot A and hot B is when we have an imbalance in load, we carry the current from the unbalanced light on the neutral wire. Let's go into the specifics for our example. Once again, we're looking at the neutral wire from the CAB to PB1. We have 2 A lights, LA1 and LA2, and we have 2 B lights. We have a balanced load, so the number of lights is 0. Let's look at PB1 to PB2. That neutral is only serving LA1. We only have 1 A light, so that number is going to be 1. PB2 to LA1, again, 1 light. It's an odd light. There's no B lights on these wires to cancel this A light out. PB1 to PB3, we have 2 B lights and 1 A light, right? So this wire is only going to carry the current from this loner B light because the LB1 and LA2 will cancel each other out. So this is going to be 1. Okay, for now we're only focusing on the A circuit, so we will not look at PB3 to LB1. Now let's look at PB3 to PB4. We are carrying 1 A light and 1 B light. The 2 will cancel each other out. There are no odd lights here. So that is going to be 0. And then PB4 to LA2 is just a single light. It's only serving LA2. There are no B lights to cancel that out. So we have 1 light. Okay, let's check our summation here. We're going to be looking at the total voltage drop over the hot A wire and the common or the neutral wire. And our threshold is 5% of 120 volts, which would be 6 volts, and we're way under that. Okay, so now for the B circuit, I'm going to take this entire table, copy it, paste it, and I'm going to run through these a little bit quickly because we've already gone through the A circuit in great detail. We're going to change that to B, and now let's enter our wire runs. We're looking at the blue wires, the hot B wires. So again, we do have CAB to PB1. We don't need PB1 to PB2 because this only serves an A light. So let's say PB1 to PB3. And then we will be looking at PB3 to LB1. And then we'll be looking at PB3 to PB5. And then we want PB5 to LB2. Okay, let's take these values down here, paste them down. We want to add a row because we want to identify PB3 to PB4 and then PB4 to PB5. So we're going to say PB3 to PB4, and then we want PB4 to PB5. Okay, so let's go through the hot B calculations. CAB to PB1, the number of B lights is 2, LB1 and LB2. PB1 to PB3, we still have 2 lights. This hot B wire is serving LB1 and LB2, so that's going to be 2. PB3 to LB1 is 1 light. PB3 to PB5 is one light because we're only serving LB2 off of that wire. And then PB5 to LB2 is one light because we're only serving LB2 off of that wire. Again, they're all 80 watts, so that equates to 0.67 amps. Distance CAB to PB1 is 8 feet. PB1 to PB3 is 156 feet. PB3 to LB1 is 50 feet. That stays the same. PB3 to PB5 is going to be 360 feet. 180 plus 180. And then PB5 to LB2 is 50 feet. So now again, on the neutral wire, if we look at CAB to PB1, we have an equal number of A lights as B lights. That's going to be 0 lights. PB1 to PB3, we have 1, 2 B lights and 1 A light. So we have an oddball out here. So that's going to be 1 light. PB3 to LB1, that's going to be 1 light because we're just serving a single light there. PB3 to PB4, we have 1 A light and 1 B light. So that's going to be 0 because it's a balanced load. The A and the B are canceling each other out. PB4 to PB5, that's going to be 1 light. PB5 to LB2, that's going to be 1 light. And then we don't need this last row here, so we can delete that. 80 watts per light. Okay, so CAB to PB1, 8 feet. PB1 to PB3, that's 156 feet. PB3 to LB1 is 50 feet. PB3 to PB4 is going to be 180. PB4 to PB5 is again 180. And PB5 to LB2 is going to be 50. And that's going to be a number 10 wire. And let's check our summation. Okay, so on the B circuit, we have 0.82 volts. We're losing 0.82 volts, well under the threshold of the 6 volts. Now, this was a pretty simple system. Maybe in the future, I will do another video showing a more complicated system. You may have a subdivision where you have multiple roads and you have multiple branches, and that can get a little bit complicated. I sincerely hope that this has helped you out. If this has been valuable to you, please leave a comment in the comments down below. I really enjoy hearing that this information has helped. You can visit my website by following the link in the description below. Thanks for watching. Have a great day and go do some great engineering. Take care.